And of course, in general, if I do not know anything about the position of my robot, then a uniform distribution will be the proper representation, and so my belief will be constant, where the constant is chosen such that the integral over my entire arena will be 1. Now let's introduce 3 important classes of localization problems. The first and easiest one is position tracking, and this is a problem we have worked on so far. So there's a known initial pose, and typically a unimodal distribution, for example, a Gaussian distribution. And then there's the problem of global localization, and this means I don't have any indication of my initial pose. And in general, in order to solve that, a unimodal distribution is not useful. Now, similar to that is a so-called kidnapped robot problem, where a global localization problem is assumed, plus there will be the possibility that someone kidnaps the robot and moves it to another place, where the robot then has to recover and determine its new global position. So now in reality, robots are not kidnapped so often, at least so far, but the practical importance of this problem is that any global localization algorithm might eventually fail, and if it does so, it needs to recover from this failure, meaning it needs the ability to discover that the position that it might have tracked for a while is completely wrong, and that therefore it needs to determine its global position again. So the practical importance is that the robot is able to recover from localization failures. So these are 3 different localization problems which are often mentioned in the standard robotics literature. Now let's think about global localization again. So we just learned that if I don't know where I am, then a uniform distribution would be the best possible choice. However, if I'm interested in modeling this with a Gaussian, another possibility would be to place a Gaussian at the center with a very large variance. So in 1D, this would mean that this is my belief. It is centered here, but that doesn't matter because I will set the variance to be very large. And so during filtering, if I integrate this with my measurement, my posterior belief will be almost the same as the probability of my measurement. And so even though I was unable to represent my initial belief exactly, I had to replace the uniform distribution by this very flat Gaussian. I eventually end up, after my first measurement, in a good guess for my system state. Now what do you think? Would it be possible to model the belief by a very wide normal distribution and subsequently rely on the measurements to determine our system state? Yes or no?